Now for the fun stuff about mass spec. We apply mechanism. Yay! Hey boy, don't you always love it when I start out a slide with that word? Recall. Oh yeah, recall this molecule that we blew to bits? Well, even though we blew it to pieces, the pieces aren't really all that random. That's the whole point of this mini lecture, to try and convince you that the fragmentation pathways do have mechanistic sense. That said, this is not beaker chemistry. I'm not going to see any primary carbocations or primary radicals in a beaker, and I don't want to see them anywhere on your exams unless you're talking mass spec. In mass spec with 70 electron volts, pretty much anything is possible. Two things you want to focus on in mass spec. First of all, there are the things that show up. That's the fragment ions that are charged. They're ions, so they have a positive charge. Those are the things that are detected and show up in the mass spec. But just as important is the piece that broke off. When a fragmentation takes place, a neutral, or it's absolutely a neutral piece, disappears, goes out the instrument. It doesn't show up, it's undetected, and the fact that it's missing can be very telling. So we will see that as we go through this. Why is this sensible? Well, because the way the molecule falls apart is completely related to the strength of the bonds in the molecule and the stability of the fragments that are formed. So hang on to that. Remember, it's all being governed by the same sorts of things you've already learned about the stability of radicals and cations and the strength of molecular bonds. Okay, the very first thing you want to do is try to imagine where that electron would be kicked out. That way you can identify the structure. This is strictly hypothetical, but you want to try and identify the structure of the molecular ion. So we know that this is the energy, relative energy levels of different kinds of electrons in a molecule. So if we have a molecule that has sigma bonds, pi bonds, and lone pairs, we know those electrons in the lone pair orbital are highest energy. Pi electrons are certainly higher than sigma electrons. Sigma electrons are buried deep within the molecule. They're the most stable. So if this thing is going to get blasted to pieces and only one electron is kicked out, if there's a lone pair, that's where it's going to come from. If there's no lone pair, then your next choice would be to lose an electron out of the pi bond. And if there's no pi bond, if it's strictly sigma bonds, then you don't have any choice. The electron is going to come out of a sigma bond. So, for example, if I look at cyclopentanone, I have pi bonds and lone pairs. Ding it with 70 electron volts, kick out an electron. What do I get? A molecular ion where I kicked an electron, bing, out of the non-bonding orbital. How about an alkyne? Well, same sort of deal. This is my easiest to kick out of orbital, so I'm going to blink an electron right out of that pi orbital, and I can identify my possible molecular orbital, my possible molecular ion is this guy. And that's really very arbitrary. I could say, put the radical on this carbon and the positive charge on this one. I could do it the other way around. You know, it's kind of whatever floats your boat. Both of those are your molecular ions, and from there you have a chance to fragment this ion in rational pathways. But before you do that, you have to figure out where that odd electron is located. Alright, so we'll start with alkanes. Alkanes, obviously, are solely sigma bonds. So here's that hexane we were talking about the other day. Turns out the base peak for hexanes is 57. Well, what do you suppose that is? Well, alright, so it turns out that we're going to play a lot with molecular weights in mass spec. Molecular weight of hexanes is, and I should just be calling it hexane, not hexanes, but in any case, C6H14, it's got a molecular weight of 86. So, the base peak, and remember, the base peak is the one that is most abundant. If it's the one that's most abundant, it means it's the most likely to form, which means it's the most stable. So the base peak is 57, which if I take 57 away from 86, that means what I'm losing is a piece that's 29. Well, 29 is bells and whistles in mass spec, because 29 adds up to the ethyl group. So, given that the base peak is 57, that implies that we could easily imagine the molecular ion being formed with the odd electron right here between C2 and C3. You know, again, we can't see this. We can only infer. But basically, that's like not much of a bond there, so it falls apart in a heartbeat. I lose the ethyl radical, neutral, not detected, and what I'm left behind with is the butyl cation, and that adds up to 57. So that's how we play the mass spec game. It's very valuable to have a sense of what typical peaks are going to show up in the mass spec and what typical fragments are lost. So for example, if we see an M-1 peak, we know we lost a hydrogen atom. M-29 means somehow or other my molecule fragmented to lose an ethyl group. M-18, that's screaming that I lost a water molecule, and so on and so forth. So, those are very common patterns in mass spec. Alright, given that, let's predict the base peak for this molecule, 2,2,4-trimethylpentane. Well, we have nothing but sigma bonds, so we could kick an odd electron out of any one of these sigma bonds. Pick one, any one. The one that's going to be plucked out is going to be the one that results in the formation of the most stable fragments. So, it stands to reason that if that bond turns into a molecular ion there, then it could just fall apart to give me the very stable tert-butyl cation, which has a mass to charge of 57. And this is probably pretty familiar because that's exactly the same molecule we looked at in the earlier mass spec video. It falls apart so easily and so quickly, there is not even a molecular ion peak. Alright, so alkanes, they're kind of all over the map. Alkenes and aromatics and alkynes, these molecules that have pi electrons, they're actually a bit more predictable. So of course it makes sense that you would lose the electrons from the pi molecular orbital. So for example, if we look at E3-hexene, there's our molecule, zap it with 70 electron volts, lose 1 electron, and we should see a molecular ion that looks like something like this, where again I could put the radical on this carbon and the cation on this one, or vice versa. What happens next? Well, it's radical chemistry. This guy is electron poor and it wants to hook up and make a bond. So what happens is it falls apart. It goes next door, forming a new double bond here and breaking that guy so that you end up with nothing. No, so that you end up with, we'll make this black, this guy. Looks pretty stable to me. Because, hey, look at that. It's an allylic cation and a methyl radical. So two things to look at. I lost a methyl radical, so I should have a substantial M-15 peak, which corresponds to this guy, C1, 2, 3, 4, 5, H 1, 2, 3, 4, 5, 6, 7, 8, 9, and whatever that adds up to is where I should see my peak in the mass spectrum. How about 1-pentyne then? Well, the starting molecular weight for 1-pentyne, 68. Pi electrons, we're going to zap an electron right out of that pi molecular orbital to get a radical cation, the molecular ion. What's going to happen? Same as before. This guy wants to hook up with somebody, so go one bond over, homolytically cleave that bond. What do you end up with? That guy. I have lost the ethyl radical, so I should see a substantial M-29 peak in my mass spectrum, or C3H3. What does that add up to? Mass to charge 39 should be present in my mass spectrum. Okay? So the base peak for this is actually results from an M-1 cleavage. You should propose a mechanism for that base peak. Alright, an aromatic example. For ethylbenzene, kick out an electron, pick a double bond, any double bond. These can be delocalized anyway, right? Once you've localized that odd electron, you would know to predict that this guy is going to pair up, cleave that guy. Holy cow, we're doing a lot of M-15 fragmentations in this particular section. That should give us this guy. Yeah, CH plus dot. And this is a huge fragmentation pathway. It's the base peak. Turns out this is mass to charge 91, and that's pretty typical, or I should say it screams aromatic. So why would that be? Well, it turns out that the benzyl cation, which as you know is very stable, well, it's more stable than you would have thought, because there's kind of a weird and magical rearrangement in mass spec that leads to the aromatic tropylium ion. So based on what we learned in chapter 14, it should make sense that this is super stable and therefore formed as a predominant base peak in the mass spectrum of aromatic compounds. Okay, I'm going to stop now because this is a lot to wrap your head around, and I will do another mini lecture on some remaining functional groups and see how they fall apart in mass spec. But remember what you want to do is locate the odd electron and then two push electrons. So that'll help you come up with rational fragmentation pathways. And ultimately what we're doing with mass spec is we're using it to confirm the structure of a molecule. Mass spec alone, that's really not very good for coming up with a structure all by itself. But with IR and NMR, use mass spec to figure out the molecular weight and nail down the structure because of reasonable fragmentation pathways. Okay, more to come.